All right, thanks for coming this morning. Kicking off LinuxFest. So first, real quick, a bit about me. I work at resin.io. We're an IoT software deployment company. It's basically in a nutshell. We'll get into that a little more because it's related to the stuff I want to talk about today. I work there as a software engineer. My background is in software engineering. I'm currently leading our DevOps team. And I've always been a hardware hobbyist. Hey. For a while now, a few years now, I've been tinkering with everything from Pis to AVR, ESP, that whole range of stuff. And I think it's a really fun space to play, but it's also challenging to do anything real or serious. And even if real or serious means something in your home that you want to use as part of home automation or whatever else, brewery automation. And then I've also always been very privacy conscious. I value my privacy. And as I love computers, and I've always loved computers, but as their pervasiveness in our community increases, like privacy becomes a bigger and bigger issue, and how to cope with that. And I think part of it is what I want to talk about, owning your own IoT. And as developers, we're in a unique position to do that. I'm on GitHub at BrownJohnF, and after this, I will post the slides and also the demo code up there. So in general, this talk will follow this flow. I want to talk about the lack of security in IoT in general, and it's a rapidly changing space. I think we're going to see a lot of improvements in the near future. I want to talk a little bit about resin.io and how that relates to the security model, and then how resinOS kind of came out of that and is something that has been given back to the community and we can use without buying into any kind of platform. And then I'll conclude with a demo of how you could basically kind of make your own like hue switch with off-the-shelf parts. So I read this quote recently, and I thought it was quite interesting, but hits the nail on the head. Right? Everything now is basically a computer that does something, rather than the old paradigm where you had tasks or projects and then you added computers to them. And it's predicted that in 2025, we will reach 75.4 billion IoT devices. And that's like roughly 10 devices per person on the planet. Right? And they're not going to be equally distributed around the planet. They're going to be hotspots. And it's going to wind up everywhere. Right? And it's already pretty much everywhere. Everything from appliances like smart fridges, wearables. That's, I think, a newer kind of space that we haven't seen much from yet. Home automation, obviously, is currently flourishing. Automotive, and it goes on and on. And this is sort of the more consumer-facing application, right? It's been everywhere, really, for years in the industrial space. And the big question for me, or a big question for me, is who's going to own these devices and the data that they're producing? Because they're going to be everywhere. They're going to be producing a ton of data. Where's that going? Who owns it? Who controls it? And then in this landscape, which I find kind of scary and intimidating, the corollary is that it's easier than ever today to actually make and operate your own IoT device as a developer. So the S in IoT stands for security, and there really isn't any. Just for fun, and this is in no way scientific, I went to Google Trends after thinking about that a little bit, and I just did a search for keywords IoT versus versus IoT security, and you can see that the IoT. This I think is a 5-year. Can't read the dates very well. 5-year window. Like IoT is really growing. IoT security is growing, but it doesn't. Again, not scientific. It doesn't seem to be growing quite the same pace. Right? Like people are more excited about IoT than they are worried about securing it right now. Then, because IoT security is really, or IoT is really included in IoT security, I just did a search for security, right? And it's trending down over the last 5 years, which I just thought was entertaining. So when we talk about the security or the threats that insecurity poses, right? I break it down kind of into these categories. And I should also say here, like, I'm not a security engineer. Like, I'm a hardware hobbyist. I'm a professional, like, sort of cloud engineer. But I break it down into thinking about in terms of compromised devices, compromised cloud services, anti-user features, and failed updates. right? And so some of these are true like security threat, and then some are just, especially the failed updates, are more about if you're not careful and you don't have security checks in place, like you open yourself up for this kind of failure mode. And so a compromised device, the two sort of obvious ones are the data exfiltration, right? And this could be data from the device, you know, if it's owned, or it could be the device collecting data from other devices on your network. You know, if you think about a lot of these connected devices don't have great inter-device security. They assume they're on a private network. So if you get access to any of those devices, you might be able to just pull down all kinds of data, you know, off the local network. And then botnets. Mirai is the big one that was involved last October with all of the outages that brought, depending on how you look at it, part of the internet down. Lizard Stressor is like a predecessor that seems to have kind of been fading. The third one, which is my personal favorite and I think the most entertaining, is assassination of your device. BrickerBot is the malware that is lately doing this a lot. And this is malware that a guy wrote, and it will infect your device. It won't do anything other than attempt to secure your device. So it has built-in support, like malware, you know, it has built-in targets, and it will find one of those targets, and if it's running default credentials, right, or on default ports, etc., it will change that, which may lock you out of your device. But its goal is to basically secure the device from yourself. But if it is unable to secure the device for whatever reason, based on type of device or something else on the device, it will nuke the device. It will brick it. And that is, I think they're estimating like something like 2 million devices that's in already. But interestingly, it's not persisted. So if you reboot the device, you're back open again, and then you may get malware, or you may get BrickerBot, or you may get one of these other ones. And then Hajim and Wi-Fetch, or Wi-Fetch, I'm not sure how to pronounce it, are predecessors to BrickerBot that are less extreme. Compromised cloud services are typical. It's what we've been dealing with since we've had the concept of cloud services, really. But IoT just means we're pushing more and more data up into that cloud, and maybe data you don't know you're pushing. And then anti-user features are, I mean, I consider it basically exfiltration of your data by the manufacturer, and usually used for things like data mining, marketing, targeting, that kind of thing. And then overprivilege, you know, giving a device access to things it doesn't need just because it's easier or the manufacturer wants it for their exfiltration purposes, etc. And then failed updates, obviously, like if you don't have a robust update mechanism, you are opening yourself up for pain. And part of this is the failure mode of a bad update, but the more the security side is that if you don't have the ability to efficiently push updates, you're going to leave devices unsecured. Right? Because nobody wants to be the engineer that's like, well, I guess we could update that, but I'm a little afraid to push it because we have a 50-50 chance of just bricking the device. Right? Like that's a bad place to be. And so I think the root causes for how we are creating this sort of poorly secured environment, the big one is remote access. You know, obviously, if you manufacture a device, it has no console, it has no access. Like that's generally much more secure. Generally, then also it's hard to update. Buggy and careless code or updates. Default credentials and open telnet are killer ones, but are incredibly common. Lack of updates, right, leaves, you know, a device may have been secure or believed to be secure when it was released. There are new vulnerabilities. Nothing's done about it. And then on device, often people are just running everything as root with no concern for do they need root. This is, you know, of course, we're talking about like a Linux capable or higher order device. And then I would consider, honestly, closed source to be a root cause of insecurity. Like it's a lot easier to be secure if you have transparent audits and the ability for people to audit their things. And you also build trust. No, we're not moving forward here. Oh, sorry about that. So how to mitigate this stuff? Again, I think we're still in the early days of people figuring out what are our best practices and what's the right way to handle this stuff. On Intel-based devices, there's Trusted Platform Module, or TPM. And then ARM has something very similar called TrustZone. Or TrustZone, I don't think is ARM specific, but there's one in ARM that's implemented on it. And these basically offload things like encryption or security or signatures to a dedicated hardware module that's much harder to compromise. And this allows the device to do things like verify updates have been signed. And you're reasonably confident that if they verify true, you can trust it because the keys to do the verification are actually in your TPM. But support for that is not widespread in the IoT sector unless you're building your own stuff. Least privilege, right? Like that's just don't give access to stuff you don't need to, or you don't need access to. And then sane security, not only at the host level, but also the application level, and vice versa, right? As everyone should be focusing on security. The cloud services are, we know, quote unquote, we know how to secure cloud services, or at least IoT doesn't really bring new things to cloud there. It just makes the targets more tempting. And then for the anti-user features, these are one of the hardest, especially when there's no transparency and you can't even tell what the device might be doing. But in general, like I try to run things on firewalled or ideally even offline networks or subnets, and that often limits their functionality. And so this ties in. These last two really are what tie into what I want to talk about today in terms of the code part, right? Like if you can deploy your own IoT devices, right? You don't have to worry about anti-user features because you're in control. And then with updates, the whole ResinOS system makes it a lot easier to do that reliably and conveniently over your home network. So I was trying to find like industry movements on this. If anyone has any others, I'd love to hear about them afterwards. But there's really only one major one I found, which is the IoT Security Foundation, and they're trying to get together some sort of consensus around what's the right way to handle this stuff and what do we do about it. And then an interesting thing that isn't really a movement, but there's an IoT Security Wiki, and their goal is to bring together everything they can about IoT and security and provide a point of reference for anyone who's starting to work on an IoT project. All right, so Resin.io. Resin.io is it's a combination of things. It's ResinOS, which is a free and open source operating system, and it's a cloud-based build and deployment pipeline, which we're in the process of open sourcing, but it's not complete. And the interesting thing about Resin compared to other players in the space is that our solution for doing the updates is using Docker. So you basically define an application and a Docker file, you ship that to us, we build it, deploy it to the device. And the problem is often, and we're attempting to solve this problem, often the last mile connectivity, right? We know how to build and test and deploy software applications when you have guaranteed connectivity, when you're running maybe even in a VM where you can do a whole VM deploy, things like that. When you get into that last mile edge device kind of space, things change. Right? You have to treat your device especially. You cannot afford to lose a device. And you need to guarantee that even if you have a failed deploy, that doesn't mean a failed device. Right? You need to isolate that. And we're seeing people use Resin successfully pretty much everywhere you can use embedded, except like fighter airplanes, like that kind of space, where I don't see Docker moving anytime soon. But that's like industrial automation, power generation. We have people using stuff underwater in sealed cases, doing wireless only over-the-air updates, all this kind of stuff. And then recently we added support so you can actually flash microcontrollers from a Resin gateway. So this is just a quick overview of how that pipeline works. So over on the far right, you'll see, I won't go into it in detail, but over on the far right, you will see the fleets of devices. So these would be the devices that are running ResinOS, and ResinOS can be connected or not. So what I want to talk about today is using it in standalone mode or local mode. Oh yeah, this is the microcontroller support. We have reference implementations for these three, and then it's basically you write your own sort of application, or you can extend. We have a Golang app that handles the updating. So ResinOS, sort of like CoreOS for embedded. How many of you here are familiar, or I guess use Docker? Is that okay? Good amount. How many of you are like actually embedded developers? Okay, a few. Yeah. So it's sort of like our goal is CoreOS, which is one of the big like Docker operating systems in the cloud space, but for embedded, right? And it's built using Yocto, which the Yocto project, which is sort of a set of build tooling. Is anyone familiar with Yocto? Yeah, so it's a toolkit, I would say, that allows you to build Linux disk images. So it's not really a distro. ResinOS is sort of a distro, but there's no necessarily like update. Or when you update, it's an atomic update. You move to the next image. Like there's no package updating. And it's basically just the minimal user space and kernel required to run Docker and a VPN client and some other components I'll touch on. So it's optimized to give as much processing capability to your application and get out of the way where it can. And it provides some nice safety guarantees, which we'll also get into, around reliability during updates of both the underlying host OS and the containers you're deploying to it. And then by using Docker in the embedded space, you also bring parity to embedded, or between embedded and cloud. Right? If you have developers that are used to writing Docker applications in the cloud, or really even, let's say, just a Node app, right? Deploying a Node app to an embedded device would be a huge pain. But if you can containerize it, right, like now you've abstracted that, and then if you can deploy that container to the embedded device, it becomes trivial. Of course, once you start interacting with actual physical hardware, things get trickier. You can't write an app that will run on a server or a Pi if you want buttons, for example. I guess maybe you could, but so ResinOS will run just out of the box. We have production builds for these devices: Raspberry Pis, BeagleBones, the Nuke. If you want to go like kind of higher end, we have a lot of people doing like digital signage with a Nuke. Upboard is an exciting new one, and then there are a bunch of more like sort of industrial focused boards. Because it's all free and open source and based on Yocto, if you have if you're comfortable with Yocto, you can easily add your own layers and build it for your target architecture. So if you use the ResinOS, one of the nice things is that it's integrated with the resin-cli. So resin-cli, this will be in the demo, right, you can interact locally with a ResinOS device on your network, and you get a lot of the sort of convenience factors of doing a deploy like on Heroku, but it's actually going to a device locally, and depending on what you're building, you may or may not even need internet access. Yeah, Yocto allows you to run it anywhere. We're using Docker in this case purely, and this is important, purely for packaging and isolation. Like, it's unwise, I think, to ever rely on Docker for security anywhere, but especially when you're doing embedded stuff and you want to interact with the hardware, your container is going to almost certainly be running in privileged mode, or at least some subset of those privileges. You're going to have access to physical peripherals. Like, you're not really getting anything about security, but you're getting isolation in the case of failure. Right? Like, you're not going to take down the rest of the system.
Can you back up one slide for just a second?
Yeah, maybe. Was that there? This one?
Yeah, I wanted that. Thank you.
And then an advantage, we have a lot of people ask, like, well, why not just use like Raspbian, right, and install Docker? Now that there's good ARM support for Docker, just do that. But ResinOS is tailored. You know, Raspbian is a general purpose operating system, and you're adding Docker to it. And out of the box, I think Raspbian will include, you know, desktop environment if you just do the standard noobs installation. But Resin really has been designed to run in the embedded space, run headless. It has a lot of features built in about, you know, surrounding reliability. Again, we'll get into a little more about that. But it's field tested. The current release is on the 2.x series. The 1.x was running in production for 2 or 3 years probably. So we saw a ton of edge cases. We saw a ton of issues. We changed some strategies in some places when we went to the 2.x release. And then it comes in a dev and prod image. I'm going to be demoing with the dev image because it's, ironically, in the security, it's not very secure, but it's really easy to work with. And the big difference is, I guess we'll get into that a little bit later, but the dev image allows you to just SSH in passwordless and exposes the Docker daemon, which is really handy for local testing. And one of the features is that we moved the logging to a RAM buffer, and so this reduces flash wear, which is one of the biggest failure modes we've seen in production devices on a device that's using flash media, like the Raspberry Pi, which is the Pi 3 is a shockingly popular production device. It's all over the place. And yeah. So here's the basic user space, right, which you touched on. We have the underlying ResinOS It's running systemd as an init system. Docker network manager for connectivity makes it really easy to drop in additional network profiles, and it will just connect. You can add multiple networks. We have some reference implementations for doing like a hotspot system. So you know, if you're giving it to someone else, they plug it in, power it up, it'll create a hotspot, they connect, they put in their Wi-Fi credentials, and then it connects to their Wi-Fi, kind of thing, or your own Wi-Fi. DNS mask for local DNS caching and for controlling the DNS servers that the device is using. Modem manager, in case you're using modem type connectivity. Avahi for local network advertising. So this, in theory, on many networks allows you to I think by default it advertises resin.local, so you can just connect to your device knowing that. It rarely works for me based on how your networks are set up. So like it wasn't working on the conference network. Dropbear for SSH, an OpenVPN. And I think it's in the production images, the OpenVPN and SSH are closed or not running. So the partition layout on disk, there's a boot partition. This contains most of the like device-specific configuration in terms of like getting the board running. The root partition, about 300 megs, and it's read-only. This is an improvement from the 1.x, the 2.x. And then we have another 300 meg empty partition. This is used for blue-green host OS updates, where we just, for those of you who aren't familiar, you just download an entire disk image, or not disk image, partition image basically for your root. You write it to the empty partition, you update your bootloader, you reboot. You basically you switch the order that you want to boot in, and so if on a successful update you'll boot into the new system, on a failure you'll just fall back to the old one and you can recover depending on how you want to handle that. Then we have a resin-conf partition. This is mounted as an overlay file system with the root. So you can put configuration in here that you want to manage, and it will persist across updates, and it will also, I mean, obviously because you can write to it while it's mounted, I guess if that makes sense. You can also, because these are downloaded as a flash image, you can also modify the image itself before writing it, you know, if you wanted to do something very custom, which we have people doing also. And then there's a data partition that will expand to fill the rest of the media. So if if you're doing something really data intensive on a Raspberry Pi for some reason and you want like a 64 gig flash card, you'll get almost 64 gigs. I guess you probably would get 63 gigs of available data storage that's read-write. That's where we put the Docker containers. And then if you want to mount volumes, etc., as part of your application, they'll be stored there. So they persist across reboots, across updates, etc. Yeah.
For blue-green OS deployments, is the bootloader smart enough to, after failing to boot, I don't know, once or a few times on the new one, go back to the old image?
Yes.
It is?
Yeah. And I don't actually know what the logic is precisely. I think it may even fall back on a single failure, but I'm not entirely sure.
Try once thing in grub, try it once.
Yeah.
So this is grub, the bootloader?
I don't think so. I think it's U-boot. Yeah. And it's possible that it varies from board to board, but I think in general it's U-boot. And I also, I don't work on the OS itself, so I'm approaching this more as a user also. So the read-only rootfs, because we don't need to go into this in detail, but the interesting things to note here are the things that, so there is some, in the resin-conf where you can modify your configuration, there are some, we only allow certain things to be modified by default. You can, of course, you can modify whatever you want before you write it to the device or after you've written it, but if you want to do that manually. But basically what we encourage is system connections in particular, so that's network manager connectivity info, your SSH keys, your Docker key, if you want to change the host name, depending on how you're running it, if you're running it connected to resin.io, we'll be running our agent on the device as well, so you can configure that. Logs, if you can, it is configurable to enable persistent logging if you want that. And yeah, other things you want to boot, things like that. So the nice thing here is that separating this out into a different partition makes it really easy to just basically reset everything. Erase that partition and it's a factory reset on the device, which is cool. So this is a graphic demonstrating the local functionality for ResinOS, which is what we're going to look at today. So from your developer machine, right, you have, this is tiny, I don't know if you can read it up there, but basically via the Resin CLI, your machine will communicate with the device as though it's like a local Docker. So you can do things like build your image, your container, and run it and things, and it's happening on your device, but it appears local. But it's, which you could do by just configuring, of course, your Docker daemon. But the Resin CLI sort of abstracts that away, and again, we'll demo it, but allows you to basically just say, like, I just want to run this, just make it run, right? And it will do intelligent things to figure out how to make that happen. All right, so this is the last little bit before we start looking at some code. The basic process for getting started with this, which I've got basically this demo set up here, but you download the ResinOS image from, I'm using the Pi 3 here. It'll come zipped, unzip it. You can see that sudo resinlocal configure resin.image. So I'll demonstrate this actually. So I need present E. So if you see here, I should have, so no resin image. Yeah, so I have resin.image there. So if I do sudo resin local configure resin.image, all right, you'll see it'll ask, what's your network SSID? Network key, advanced settings. By the way, these won't work, but so you can set the host name here, LinuxFest. Persistent logging by default is off, but you can enable it here if you want. And then it's written the image.
What are you communicating with right here? The code that you're running?
So this is a CLI written. It's a Node,
Okay.
Node client, yeah, and it will do. It'll do a lot of things. Like I'm using this in the local mode, as you can see, resin local configure. You can run this non-locally, and then it will also authenticate you with the Resin API, and then it will allow you to actually provision your device, and then it'll come online, and you can manage it via the Resin UI and everything else.
So you're building an image that you'll eventually move to your device.
So in this case, what I'm doing is actually just configuring it. So this .img file is actually, it's writable. It's a disk image. Basically, you could write it with DD or echar or something like that. And what this is doing behind the scenes, which this is a newer feature, and we used to do it manually. It's basically mounting as like a loopback interface. It's mounting the partition in the disk image that is the configuration, and then it's interactively asking you what you want to set, and then behind the scenes it's actually going and writing files in that partition, and then at the end it unmounts it, and then you have your image. So it just...
So that's why you had to sudo it, because there's a mount.
Exactly, yeah, because well, not only are you mounting it, but inside the mount those files are owned by root because it's the disk image. So they'll be, yeah.
So this is on your laptop then?
Yeah, so this is all running right now on my laptop.
So the Resin application that you're calling as sudo, is that something installed from
Yes.
the package manager?
Yeah, so that I did well, no, it's not in a package manner. I did a sudo install G. I think it's resin CLI.
Okay.
Yeah. Yeah, I guess I left that out of the instructions. Alright. So then, again, as a convenience function, we have this resin local flash resin.image. And this will basically do something similar. It will look for devices. Are any of you familiar with Echar, the SD card writing software? It's another Resin project. We had a ton of problems onboarding people where they were struggling to write their SD cards, especially across all these different operating systems. And we wound up dealing with it enough that we decided we should just write a cross-platform tool. So that tool is called Echar. It's a CLI and a GUI. It's got a lot of cool functionality. anyway, outside the scope of this talk, but it's worth checking out. And under the hood, I believe the CLI uses the libraries that are used in Echar to do this. So it will interactively say, I don't see any devices, please plug one in. You stick an SD card into your computer. It'll say like, oh, here's one. Is this the one you want to write? You say yes. It'll write it. It'll checksum it. It'll verify it, etc. So it's very nice. So you write that to your SD card. Sorry, for some reason the slides are very laggy here. Come on. There we go. You boot the device and then connect over the local network. If you're lucky, you can just do resin.local. I usually wind up doing an ARP scan and looking for the, it's really convenient if you already know the MAC address of the device you're trying to connect to. But otherwise, if it's a home network, I did it at the conference, and it was like a huge list of Raspberry Pis that showed up. But generally, there's only like a few. And you can make a guess about which one's yours. And then by default, we run SSH on port 22222. It's 5 2s. And that's because a lot of user applications run their own SSH inside the container. By default, when you're using the production image, the host SSH will be disabled. And so you would, if you want to SSH into your own device, you'd need to put SSH into your container and basically deploy it, and then you can go in that way. I mean, in theory, you would have, if you leave SSH enabled on the host OS, you would have the key somewhere, but it's not what you should be using to debug, for example. Or at least not in production. Okay, so we've done all that, right? I have my device online. And is that, how's the font size? Should I go larger, smaller? Good? Okay. So here I am in my LinuxFest presentation code repository. I have a very simple, I broke out the app into a few stages that we'll deploy, like one by one, which is why there's 1 through 4. And then app is the one that I'll just copy them into to do the deploy as a demonstration. But in theory, right, I have my app.js file, I have a Docker file, I have node modules, which I don't really need locally because I'm not running it locally. I have a package.json and then tags because I use C tags. So we go here, take a look. Here's my app 1, right? I'm using strict mode. I'm going to log console hello world, right? So if I come over here, here's the command that I would use to say I want to run this on my device. I'm going to say sudo resinlocalpush. The sudo here is an artifact. We're working on removing that because there are reasons why you currently need sudo, but they're not great ones, and so that's in the works. And I want to push it to, this is the IP address, which I looked up before this started, of my device, and the S is the source. I should use the long form, but source, I want this directory, right? So that's going to do a build of a Docker file. So if I go here, this is the Docker file that I'm going to build. So I'm using one of the ResinOS base images, which I guess I didn't touch on earlier. So we maintain over 500 ARM, well, mostly ARM and Intel Nuke base images for our customers and the community and anybody who wants to use it. It does not have to be used on ResinOS, but we basically have a build matrix, and so I think we do Fedora, Debian, and Alpine, and then we do several different language runtimes, and then we do like basic, just stock Debian, different versions of Debian, versions of Alpine, different versions of Fedora, and that's all sort of put into a build matrix, and so you can select what you want. So here I want Raspberry Pi 3 and their device specific. So Raspberry Pi 3 node and node 7. All right. My entry point, this is what I want my container to run. So I'm just going to run npm, and I'm going to run npm start. And my working directory is source, and I'll add package.json. I'll run npm install, and then I'll copy my app.js into the folder, which is right here. All right. So when I hit this, I see that it's syncing. So resin-localpush is smart enough to know whether it needs to just sync your files into a running container or whether it needs to actually build that container from scratch. So in this case, it knew that because I've pushed prior iterations of this, all it needed to do was basically synchronize app.js across into that container. So it tells me it completed successfully, and then it streams the logs from your container, which is really nice. In this case, my container exited, right? So on the device, actually we can do that. Let's do this. Is this the right device? Yes. If I do docker ps, it's formatted not very well. You'll see it's up 2 seconds. Now it's restarting, right? So the Docker daemon is maintaining my application. It's continuing to reboot it or boot it after it crashes. Well, not crashes, after it exits, right? Which is generally what you want on an embedded device. You can change that if you want to. So now let's go back in here and say like, hello, LinuxFest. Oops, not that. Right, push it again. We should get the same thing, except we'll get the different output. Boots up. Hello, LinuxFest. All right. Now again, this device could be in my basement. This is a common use case for me. I have various devices monitoring various things that could go horribly wrong in my basement. In this case, it's right here. So now let's move. I'm just going to copy app to app, and now we get a little more interesting. All right, I'm sorry the resolution is so low. I thought the projectors would be a little higher. So we'll walk through this real quick. How many of you are Node or JavaScript or developers are comfortable and familiar? Okay, so not a ton, so I'll go through it a little bit. So we're requiring the libraries we're using. I'm using promises because I find it much more readable. HueJ is a library for interacting with the Philips Hue bridge, which I have here. RPIO is a library for the Raspberry Pi GPIO pins. There are a bunch. This is one that I enjoy. It's pretty straightforward. I'm configuring my Hue username, which is also the password. A little strange. Using environment variables. I am then defining a function here called connect, and let's see, let's just go down a little bit. All this function does is basically discover bridges on the local network using HueJ, so HueJ.discover, and then if there are no bridges, it's going to throw an error. Otherwise, it's going to log the info about that bridge. It's going to start a new client for the bridge using the first bridge it found, which hopefully there's one, and or the first one is my bridge. And then it's going to verify it's authenticated, and if it is, print authenticated. All right. Then all we're going to do is define a function called run that's going to call connect and catch any errors and output them and exit, and then we're going to execute run. Everybody clear? So I do the same push. Start up, boom. Found a bridge and we're authenticated. Thank God. So the environment variables, right, are one thing that we haven't looked at yet. If you look, there are a lot of hidden files in here, but there's one called resin-sync.yaml. So if we look at this, right, this is how the resin sync, the resin push, resin sync, knows how to do the push, whether it needs to do a build from scratch or whether it can just sync files across. So I have an app name which I defined. You can also run multiple apps on one device by setting their app name. I have certain build triggers. There's a mode in which you can watch for changes, I believe, and it'll sync them across. So this is used for that, but it's also used, if you look at, there's a Dockerfile and a package.json checksums. If these it checks these checksums every time I do a sync or a push. And if these have changed, it knows that it must rebuild the Docker file. Right? And that's, if you're familiar with Docker, that'll be clear. If not, that's because of the way Docker builds an image, which is basically it's basically just a disk image that can be run. It builds it in order, and it applies the layers as diffs or changes on top of the layer preceding. So in this case, my package.json appears up in the file before I run npm install. So if I change my package.json and I just sync that across, nothing's going to happen, right? Because I'm not going to run npm install unless I rebuild my Docker container. So it knows that if the package.json changes, it needs to do a complete rebuild. The same is true of my Docker file. If my Docker file changes, I need to do a complete rebuild. Docker will also attempt to cache layers internally when it's doing builds. So if I only change my app.js line, which I'll do also later, you'll see that it will only, it'll be a really quick rebuild, and it won't necessarily have to run the whole npm install process again. Okay, so then continuing on, we have environment. This will have to be changed. You can ignore these. These are from old projects. So Hue username, this is how I'm setting that environment variable. Makes sense. And then I have some things I want to ignore. Like I do not want to ever sync my .git or my node modules folder across. You could, in theory, sync your node modules if you were running compatible architecture between your devices. And really, you should probably then have the same operating system. And so it's much better just not to do that and let it be handled by doing an actual build natively.
Question.
Yeah.
That Hue username, is that an SSH key or is that just a random?
I believe it's just like a UUID that so you can get that off of the Hue bridge. I didn't want to get too Hue specific when I was demoing, but it's kind of a strange process. Yeah, you make an API call, or I think they even have a little web interface, and you basically say add a user, and then within 30 seconds you have to like hit this button on top of the device to prove that you're actually in control of the device, and then they give you that. And then it's your username and authentication. It's basically an API token. But, yeah. All right. So now that we've done that, let's move on to, I think we're on app 3. Okay, so app 3 is similar. All right, I've added Lodash. I don't know why. I don't think I'm using it here. Now I'm starting to interact with the hardware. So I'm adding a pin. So my setup here, let me give some context. I've got a little tiny breadboard. I've got 3 buttons on it. Right, they're connected to the GPIO pins of the Pi. So I have the buttons, and then I have power, 3 volt coming in here. So they're normally closed. No, normally open. Sorry. When I press it, it'll close it. We'll send a signal to the pin. What I want to do is I want the middle button here to turn the light on and off. Right. So the use case for this, and this is actually something I'm working on in my house right now. I want, like, Hue is cool, but you don't want to constantly be pulling your app in and out. Like, I want switches, and I don't want to go buy the Hue switches, right? Just because they're expensive, and I could do this, and maybe I want to add multi-function switches. Press and hold, it does the Hue. Press it once, it does something else, etc. So I define the pin that I'm using there. I do the same connect function. It's unchanged. But now I'm adding this function called watch. And this basically takes a client, which is what we're returning from that authenticate function, or connect function. And then it's getting all my groups of lights, which in this case I only have one here demoing. And then it's opening that on-off pin for input and activating the pull-down resistor. So this is a nice feature about this library, and it's the feature of the Pi, but the library uses it. The Pi GPIO chip has built-in pull-up and down resistors, so you don't have to add them to your circuit unless you're doing something special. And then I'm just going to pull, and I think it pulls one every millisecond. It just sees if the circuit's been closed, and if the pin, this return function here is saying that if the pin is being released, or if the change was that the circuit's broken, I don't want to do anything. So like I want it to activate on the press of the button and then not the release. Right? And then for each group of lights, I'm going to just toggle whether they're on or off, and then save that, which makes the actual API call. And then once I've set up this polling, I'm going to log ready, so I know I can hit the button. And then all I did was extend the run function. And this is using promise chaining. So I'm connecting, and then I'm going to watch, and same error catching. So we go.
Basically toggling the light, right?
Yes, exactly. Yep. I don't care what state it's in. I just want it to be the other one. So do the same sync. Uh-oh. What do we got here? Oh. All right. I was going to say, I didn't think I was using Lodash. So one thing to note here also is that I'm saving, but I'm not committing. So this is really nice. Like, we encourage people, even if you're using the Resin actually hosted deployment platform, this is the best way to do local development, because I don't have to keep committing things and pushing them and waiting for builds, and like I can just do this really quickly. All right, and now, in theory, if I press this middle button, we get the light to come on. Yeah, magic. You hit it again. My wife can attest that actually I really like hitting the button over and over again while she's trying to read in the living room. All right, so now.
Don't you need to measure the granularity period, how long you push it? Sometimes you just trigger it fast.
Switch
Oh,
bounds.
yeah.
Switch bounds.
Well, right now I'm not.
Okay.
I've noticed it, like normally, yeah, you would have to. The polling with the RPIO library, the polling seems to be pretty good. So basically, when I was doing this demo, I was expecting that now I would have to write debounce code, and I was like, well, actually, it works fine. So
it's protected by the library.
well, I don't know that for sure. I have every now and then, like if I've tried to do it really quickly, I've seen some strange behavior. But by and large, it's been very solid. It may be that because it's polling every millisecond, that because it's a poll and not a true like interrupt, it may actually be desensitized enough. But I'm not. Yeah, it's demo code. Okay, so then we'll do this last one a little differently. So app 4. What? Okay, this tiny screen is very confusing. So now the next thing I want to do is I want to be able to dim and brighten the lights, right, from my physical switch. So I've got these two buttons on either side connected to two more pins. I want to be able to hit the right one and have it go brighter, and the left one and have it go dimmer. So I'm using the same libraries. I've defined some more pins. One challenging thing with using Pi libraries in general is figuring out which pin number they want. You mess that, because there are multiple. You can use the Broadcom pin, or you can use the Pi pin number. I'm doing the same connect function. My watch function is now extended pretty trivially and naively here. So I'm doing my same watch, the polling for the on-off pin, right, and turning it on and off. But now I have two basically duplicate code blocks, one for the dim pin and one for the brighten pin. And they're doing something very similar. They're looping through all the groups and making a change, except instead of just toggling on-off, they're setting the brightness to the current brightness minus 20. And the hue uses a brightness, an integer brightness value from 0 to 254. So I'm just subtracting 20 if it's dim, and then I'm checking if I've gone below 0. If it's below 0, I'm just going to set it to 0. And I'm going to log that for debugging. And then I'm going to turn the light on also, actually. So if it's off and I just turn the dim up, I want the light to come on, or down, honestly. And transition time, I don't know if you noticed when you turn it on and off, it kind of has a fade to it. I found that with the dimming, you often want to hit it a few times, and with the fade, it's really obnoxious. And then you do get some strange, it's not a debounce, but you get basically like an API lag, and it was throwing some errors, and it doesn't like it. So I shorten the transition time. And then I do the same, save the group. And you can see that, well, the next function does basically exactly the same thing, but it brightens it.
Is there reason iterate through all the groups? It implies more than one.
Yeah, well, when I was setting this up, I was in my house, and I had several rooms, and I was sometimes working on it in different rooms, and so I just, basically, this would simulate, the other thing is like, part of what I want this for is when I go to bed, I just want to hit a button and have all the lights go out. I don't want to have my phone necessarily, or I've gotten into bed and I don't have to like pull my phone out. But yeah, realistically, you'd probably want them attached to the room, and you'd have an environment variable that would configure which group you want. And the Hue API provides the ability to go through and say, here are all of my, let me find the group with this name. So you could say, you know, turn on and off the living room, and that would work. So all I've done is add that. But now, instead of just syncing this code, let's actually change our package.json file. And if you saw my Docker file, I just said npm start. So that's set here in the scripts. So instead, I'm going to do app4. Right? Oops. And then, because my Docker file is, I need app4 present in the container, right? I'm going to change this to app4. So I'll kill the logs there. You notice the logs were persisted there because my application isn't crashing and exiting. So now I'm going to do the push again. What we see now, instead of syncing, we see building. So this is where the resin-cli noticed that actually I changed both of my important files, dockerfile and package.json.
Is that building locally, or is that building on?
It's building on the device.
On the device.
Yeah. And so this avoids the whole cross-compilation problem. At the price of being incredibly slow, depending on what you're doing. I was talking to somebody who was building like some sort of SciPy or something, and it took him like 6 hours on his Pi to build. Yeah. So.
You better arm emulators.
Yeah, you do. We build for the cloud platform. We build on KeyMove virtualization. And we have some patches, some of which we've upstreamed and some we're keeping proprietary for improving speed and reliability of cross-architecture Docker builds.
Do you see much in the way of pre-built packages? I mean, it's like a Pi library, you know it's for a Pi, and they could just have a pre-built binary in that?
It depends a lot on the use case. If it's somebody's personal code, then yes. But third-party, a lot of people like don't want to just pull a binary down. If you have a binary that you trust, you know, that you trust the organization, you have a checksum, then yeah, we do that actually for some of our own internal, not even on device images. You know, like we know that we've audited this package at this checksum, and so our Docker build, instead of building it, we'll pull it and checksum it. Yeah.
Yeah, you see it with the Protractor, which is like an online EDW test library.
Okay.
Just pre-builds for every platform.
Yeah. So here you're seeing Docker logs for the build process, and you'll see it's using the cache until it gets to the copy package.json. Now it's running it. Now we have to do the npm install. We have to build some native extensions for the GPIO connectivity.
Is the light directly connected to RPI?
The light?
Yeah, the lamp.
No, the lamp is just plugged into the wall.
Oh.
So the lamp is, I guess the Philips Hue uses, I think it's Z-Wave or Zigbee to connect with their bridge.
Oh.
Yeah. When I originally came up with this talk, what I was thinking would be cool is to create a bridge emulator that would connect to the lights directly. But then I decided the scope of that is really beyond what would make a good demo. Yeah.
So what is ResinOS starting when it just powers on? Is it every Docker image that's been deployed to it? Or does that configure somewhere?
That's a really good question. By default, it will do whatever container was currently running when it was powered off.
So can you have more than one container running at a time?
You can, yeah. Basically, if you're using ResinOS like I'm using it here in standalone mode, there's no sort of magic happening on the device. We're just using native Docker daemon functionality. So we're running a container, but we're connecting remotely to the device and running a container, and we're saying I want it to automatically restart and I want it to start on boot. And so yeah, you should be able to do a different application, give it a different name, or you'll have a conflict, and deploy that, and then they'll both be running. All right, so now it's deployed. Let's make sure our original functionality still works. Excellent. And then let's see if we can turn it down. Oh, we did. But now, I don't know if can you guys see that? It's not very sensitive. You also see on the logs, I'm seeing the values. Oh, it's a little clipped. Yeah, so there's 3. And then there's also brighten, so I can take it up. But that's a little weak, so let's go back. And app 4, and let's say instead of 20, let's do, what, 70. It's a less useful dimmer, but. Push, and now we should see it just be a sync because all we did was change our app. And there we go. Wait for it to be ready. This is the most painful part. Come on. Okay. And there we have a much more aggressive dim. A little laggy. Not a great experience, but functional. All right. So that's about it. I think we've about hit time. But yeah, welcome questions.
What is the device at the light that's controlling?
What is what?
What is actually controlling the bulb?
Oh, so this Philips Hue bridge is actually controlling the bulb.
What's the device at the bulb?
Oh, so the bulb, the Philips Hue has an the bulb is integrated with a wireless connectivity. It's like a I don't know the details of the protocol, but it's Z-Wave or Zigbee, and it's used commonly in home automation, I think, and it can do it in mesh. Yeah, so it's not online, but it's a local radio connection to the hub, but it's built into the base of the bulb, so you can put it into any light socket. Yeah, this is just a lamp that I had on my desk that's convenient to travel with. It's cast iron.
What's the range on
The Zigbee? I have no. I don't know, but I believe it's pretty long range. It's whole house, at least. I don't know if it would work across buildings.
Question.
Yes?
For a hobbyist who wants to play with this at home, rough idea of skill sets? How much Docker do you need to know, for example?
Depends on what you want to do. If you wanted to take this and sort of extend it,
yes.
Almost no Docker.
Okay.
And Resin has great docs for. The nice thing about this is that the pattern for your application is basically identical with what you'd use with the commercial resin.io offering. So all the documentation for getting code working is applicable. You just don't have to be a customer. Yeah. Thanks.